Good morning and welcome back to Blue Waters webinars. This is Maxim Belkin with the Blue Waters Project, and today I'm pleased to welcome you to a new edition in our Scientific Software Ecosystems track. The title of today's webinar is the SDE, a General Computational Chemistry Software Framework, and it will be presented by Ryan Richard, an associate scientist at the Ames Laboratory. Ryan received his PhD in chemistry from the Ohio State University, and currently he is working on the open source electronic structure package NWChem-EX. As always, I'd like to remind everyone that you can post questions to Ryan through the YouTube live chat as well as our Slack channel. Information on how to join our Slack channel can be found in the sidebar below. With that, thank you, Ryan, for joining us today, and take it away.
Thanks. So, to start with, I guess, what is computational chemistry? What is sort of the problems we're trying to solve? So as the name hopefully suggests, the idea is we are using computations to predict and explain chemistry. And in practice, we can do this quite accurately. So what these acronyms mean is sort of irrelevant, but this green one here usually can predict experiments to within about 1 kcal, which is accurate enough to predict chemistry. Unfortunately, what this also shows you is the scaling. So if you're familiar with computer algorithms in general, something like Quicksort's way down here, and you can see we're very quickly hitting a high cost. So what does that mean? Typically, we have to employ either approximations to these methods and/or we have to use HPC resources. And how we do this is an ongoing moving target. And so this is sort of the motivation for the SDE originally, was to how do we get a framework to build our computational chemistry program on that is easy to refactor, so that when we target the next HPC system or a new approximation, we can switch this out. It also comes into play that because this becomes very modular, it becomes very easy to adopt other libraries in the field of computational chemistry, as well as share our libraries. So it also has an interoperability component to it. If you're not familiar with computational chemistry, there's a plethora of packages out there. NWChem was our original package. It's being redesigned from the ground up for the Exascale as part of the Department of Energy's Exascale Computing Project. That's what NWChem-X is. So the SDE itself is supposed to be a sort of very general idea on this slide. So each algorithm gets written in sort of its own little module. You can think of it as this box. Then when you need something, you end up calling other modules. So what we've done is essentially set up a double dispatch pattern. So the first dispatch occurs on what is the property you're trying to compute. We call that the property type. So in this particular case, property types are given by these green boxes. So energy method is a property type for anything that can compute in energy. And then the second dispatch occurs on the algorithm. So in this particular case, we have an algorithm that optimizes the geometry and then returns the energy of the optimized geometry. We have also a bunch of other methods that we can use to compute the energy. And so ultimately, the SDE is capable of doing double dispatch, the property type as well as the implementation. And yeah, because it's modular, we can contribute back to the ecosystem of computational chemistry. It's our hope that people will adopt some of these modules that we write, particularly since we're already tuning them for high performance computing. This will allow other packages to immediately benefit from that work. It also means it's easy to rapid prototype. You can simply go grab a library that's out there, plug it in. We've also got a Python API, so you can write your module in Python, and it just goes right in. No need to recompile. I'm going to actually skip this part because I'm going to show you a tutorial. That's worth mentioning though, because I'm not sure it comes up in the tutorial. The way this modular system works, the actual framework, the SDE, is essentially assembling a call graph, and it has to determine what data to move around and all that good stuff. And as a result, it can keep track of the inputs to each module as well as the outputs. And so you can use a technique known as memoization to actually checkpoint the calculation, which, if you're familiar at all with computational chemistry packages, you know that the vast majority of them have no checkpointing capabilities whatsoever. So if your 2-week calculation dies a week in, you lost a week of computational time. We're changing that with NWChemX. And yeah, I'll just skip this stuff. That's sort of the background. And now I'm going to jump over to the tutorials. And hopefully the tutorials will also make some of these concepts a lot more clear. So I figured I'd start with how do we declare a property type within the SDE. And for the purposes of this tutorial, I sort of removed myself from computational chemistry. We're going to be writing property types that compute the area of a shape and the volume of a prism. And so yeah, this tutorial is actually taken from the SDE manual. The SDE is meant to be a general C++ framework for doing double dispatch, also known as the asynchronous visitor pattern, if you're familiar with patterns like that. It actually works without doing multiple inheritance, which is the usual way you would do the asynchronous visitor pattern, and multiple inheritance has all sorts of wonderful problems in C++, which is why we actually wrote the SDE to avoid that. Anyways, back to the property type tutorial. So to declare a property type, you just need to include the property type header. Then it uses the curiously recurring template pattern to instantiate your property type. So you inherit from the property type, which is templated on the name of the property type you're implemented. And that basically does a bunch of fun things using template metaprogramming to extract some information off your property type at compile time. And so every property type can be thought of as defining essentially a function API. So there's really two parts to a function API. It's what it takes, the inputs, and what it returns, the results. So your property type also has to declare two functions. The first one is inputs, and it's going to define what your function takes as input. So scrolling down a little bit, the syntax for this is you call this function from your base class, and then it returns some object that's got a really nasty type. You don't want to think about it. And then we're going to declare two fields. So essentially we're declaring a function that takes two doubles, and we sort of adopted a Python Quark strategy here. So associated with each one of these arguments is also going to be a keyword. So the first one's going to be called dimension 1, the second one's going to be called dimension 2. And so we're implementing the area property type. So dimension 1 is going to be the first dimension of our shape. Dimension 2 is going to be the second dimension of our shape. And we also allow you to do some, put some metadata associated with these dimensions. So here we set these very useful descriptions: the length of the first dimension, the length of the second dimension. And we'll later overwrite these when we have a more concrete implementation. Property types basically are abstract base classes, so it's hard to say anything concrete about the inputs. And then we just return this nasty typed object, and we're done declaring inputs. Declaring the returns works very similar. We use a function called results, and you again use this function declare result, gives you some nasty type. You declare, in this case, it returns a single double. Again, there's sort of a Quarks thing going on. So we associate the key area with it. So our area property type takes two doubles, returns a double, and that returned double is the area of the shape. And we go ahead and also set some metadata so you know that that is the description of that area. So I forgot I need to update this tutorial. We actually are defining 3 property types. We're also going to define this perimeter property type, which, as you can imagine, calculates the perimeter of a shape. The declaration is very similar to the area. Our shape has 2 dimensions. The only difference here is instead of returning an area, it returns a perimeter, but that's also a double. Prism volume is a little bit more interesting because we're going to return 2 things. So in general, you're not limited to a single return. You can do multiple returns. So here we're going to return the area of the base as well as the volume of the prism. So that's really all there is to declaring a property type. It's basically just declaring the inputs and the outputs sort of following this boilerplate. The more interesting thing is when we declare modules. So this tutorial walks us through how do you declare a module. So these are the implementations on that to dispatch sort of paradigm. So I remind you how to calculate the area and the perimeter. And so we're going to start with declaring a module that computes the area and perimeter of a rectangle. So all modules inherit from this common base class module base. And the constructor, the constructor takes your this pointer and then it does a little bit of it's not meta template programming anymore. It's done at runtime, but it extracts the type of your class off of it. Let's see. Anyways, so then we have to declare the inputs to our module. So the module can take different. So because it's satisfying the area and the perimeter. Because it's actually satisfying the area and perimeter property types, it minimally has to take the inputs of the area and the perimeter property types, but it can take additional arguments. And I show that below. So generally what that means is you would have something that's basically a bunch of boilerplate where you replicate the dimension. So in this case, you would have to say, okay, it takes dimension 1, takes dimension 2, computes an area and a perimeter. But we can get all that information actually from the property types. So we define this convenience function, satisfies property type. And so this will do some meta template programming and basically look at area and perimeter, figure out it's part meta template programming. I'm fine with that. So it figures out what area and perimeter satisfies, and now this automatically registers all of those inputs and all of those returns. And you can also set metadata associated with the module. So here we say, okay, the area module is going to compute the area of a rectangle. Again, I should update these tutorials so that it says it also computes the perimeter. I can give citations. I have no idea who actually figured out how to compute the area of a rectangle. I gave credit to Euclid. And so here's an example of how you can set additional inputs and results. So this is all still within the constructor of the module class. So I decided that it also takes an input, the name of the rectangle, sort of grasping at straws for what else a rectangle class would have to take. And it's going to return a summary which uses that name. And as I had also mentioned with the property types, we can now change the descriptions of those inputs to make them more user-friendly. So in this particular case, we say that dimension 1 is the height of the rectangle and dimension 2 is the width of the rectangle. And so that ends our constructor. Then the other part of a module is this run function. So all modules have to implement this run function, which basically takes a Quargs map. These are all those inputs that the user set, also synchronized with whatever defaults you set in the constructor up there, which I didn't set any defaults. It also takes submodules. I'll get to the submodules when we talk about the volume, the prism volume. For now, just ignore that. And it returns a result map. Result map is basically, again, a sort of a Quargs thing. It's a little bit different than an input map because the results are going to be memoized. So first thing you would do is actually, again, you have this sort of map thing. For convenience, we wrote these arguments or these functions that will quickly unwrap those into your arguments. It does use C++17. Well, in this syntax, it uses 17. I guess there's nothing to stop you from using like std_tie here if you don't want to use 17. But the idea is an area took two inputs, dimension 1, dimension 2, and as we said in the constructor, we're interpreting them as the base and the height. And so this automatically unwraps those into these two variables, and we can now just use these variables. And we can do the same thing for perimeter. We don't really gain anything because perimeter takes the same inputs as area, but in general, you would have to do this for every property type you satisfy. Then so there's also that other input name, which is not actually part of any of the property types, so we have to unwrap that one manually. So the actual inputs, those chords-like maps, use the C++ technique of type erasure. So you grab it, you get some type erased object back, and then you have to cast it. And so we adopted this syntax. So you pass the type you want to get it back as. And so now you have the name of it. So then we actually have to implement the module. So we have our inputs. These compute the area, the perimeter, and the summary. Not that interesting. And so once you've done your algorithm, the next step is to actually return all the results so that people can use them. So the way you do this is you declare a results object, and we have similar functions like we did for the unwrapping the inputs. We have functions for wrapping the results. And so you just call it for every property type again. So, and they also chain, so that's why you have to pass the result. So this is basically taking a union of all the results into the result map that gets returned. So area, as we said, returns an area, so we give it the area volume, or the area value. The perimeter returns the perimeter, so we gave it the perimeter value we computed up above. And then we have to manually add that summary because, again, none of those property types also had that return. And we add the result we add it to the result and return it. So that's the end of our rectangle module. The prism module is going to compute the volume of a prism, and it's going to do this by using a submodule. And so this introduces how you can work with submodules. So the beginning of the constructor is the same as it sort of was for the rectangle. We say it satisfies property type prism volume. We give a description, citation. Again, I'm giving Euclid all sorts of credit for things. I don't know if he did it or not. And then we change the input description so it's a little bit more useful. So here I glanced over it in the prism volume constructor, but the input is actually an std vector. And so the first element, or the first two elements we say are going to be used for the dimensions of the base, and the last is going to be the height of our prism. So again, just setting a more useful description for the input. And the new feature here is that we're going to use a submodule. So basically a prism is nothing more than the area of the base times the height. And so rather than tying or coupling the prism to the formula used for the area, what we're going to do is we're going to take a submodule that computes an area, use that result, and then multiply it by the height. Again, this is sort of a very toy example, but it's meant to hopefully illustrate the idea of how you end up building a program. So the coupling occurs on a property type, on a per property type basis. It's not coupled to the underlying implementation. And this is really the trick to all of the interoperability. So in this particular case, if I had some massively parallel algorithm for computing the area, I could use it without knowing that I'm using the massively parallel algorithm. Or I could use one from electronic structure package X or Y, whatever. There's no coupling to the actual implementation. The coupling is only to what that implementation computes. And so how do we do this? Well, we use this add submodule function here. So we said we're going to add a submodule. That submodule has to satisfy the property type area. We have to give a key for getting the submodule back. In general, you can have a whole bunch of submodules, and we need to be able to distinguish between the submodules. And we add a description of what we're going to use the submodule for. A lot of times the property type is sufficient, but sometimes you can have either multiple property types, or you can have multiple instances of the same property type, or you just want to give a more clear description. So here we say it's the bases area. I don't know if that's really any more clear, but there you go. We added a description. And so that ends the constructor for the Prism class. And now we're going to implement the actual module. So now the sort of new feature relative to the rectangle class is that we are going to be able to use those submodules. So now this submodules array is going to be significant. Our first step is the same as it was for the rectangle. We're going to unwrap these type erased inputs. And this does highlight that I actually allow you to pass constant reference data through the API, so you don't have to do copies. It's particularly important in electronic structure theory because we're passing huge tensors all over the place. So the first thing we do now that we have our dimensions is we're going to actually pass them to that submodule. So to do that, that submodule that comes in as the part of the input accepts we ask for the area submodule, and then that submodule that comes back is again sort of an abstract thing, and it can satisfy multiple property types. In fact, the rectangle class, if that's the module we get back, actually satisfies the area and the perimeter property type. And so we need to know which property type to run it as. So that's what this call does. It says run it as the area property type, and provided these arguments. And so these come from that the actual input to the Prism module. We'll pass them now to the area. The area module does its thing and returns us an area. And we never have to know the details of how the area module actually worked. And then we go on to actually compute the volume. As promised, it's nothing more than the area times the height. And the only slightly new thing here is we can wrap multiple results, because again, we're returning two things. We return the area of the base and the volume. So that's how you declare a module base. That's how you declare a module using the module base class. So the last tutorial I have, so there's no way I'm going to hit an hour. This is not going to take me 40 minutes, is what does this look like at the top level? And this is sort of the workflow level, the C++ level. There is a Python API over it. It really doesn't look too much different in the grand scheme of things. At some point we will add a tutorial for it. Still working on the bindings and automating them a little bit at the moment. Anyways, so the first thing you have to do is actually tell the module manager about all the modules that your library provides. So it's assumed that, for example, you created a geometry library that, in addition to that rectangle and prism module we just developed, you maybe made a bunch of others. And so for convenience, we recommend that every library defines this function load modules, which takes a module manager, which is an object that, as the name suggests, manages the modules. And so it's ultimately the thing that's responsible for figuring out what submodules your module will end up calling, figuring out what's available, what depends on what. It does all those wonderful things. And what you have to do is just let it know about your modules. And the way you do this is it has a function add module. You give it a key. And this is just a convenience thing for the user. So if the user wants to specifically use your module, they use these keys. In general, they would probably be more descriptive than the same as the name of the class. So for example, if NWChemX was releasing this, we would call this like the NWChemX rectangle or something. That way it doesn't get confused with, say, electronic structure package X's rectangle. Because it's likely that multiple electronic structure packages are going to implement the same algorithm, possibly in a slightly different way. And so you want to be able to distinguish them just based on the strings. So it's important that these strings are more descriptive than this. And then you actually just instantiate a shared pointer to your module. And that's all you need to do. So you do it for the rectangle, you do it for the prism. And one of the other, so that's all you need to do, to add the modules. What it's also recommended is if you introduce a new property type, which it is assumed that this geometry module is introducing the area and the prism volume property types, you should also set a default. This way the user doesn't have to manually go through and set all the modules. So whenever somebody needs an area, you recommend that they use the rectangle module, and whenever they need a prism volume, they use the prism. Probably a very silly default because, of course, not everyone's going to want to compute the area of a rectangle, but you get the idea. So now that you've defined, that load module goes in your library. And so now this is actually what a user would see. So if you're doing, you can do this all in C++. So this would be your actual main function. I called it example main, but it doesn't really matter. So the first thing you do is you instantiate a module manager, and then you would call load modules from all of the libraries you want to use. In particular, NWChemX, of course, is going to provide a single load modules function for you. So you load all of NWChemX's modules at once. So you really only have to call load modules if you're using other electronic structure packages as well. Then with that, you can go ahead and change the inputs to the modules. So recall that rectangle had this extra argument name. Since none of the property types actually have name set, the only way to set it is to bind the argument. So that's what this change input does, is it binds an argument to a particular module, and it's to a particular instance of a module, I should state. So if anytime someone uses the module that has the key rectangle, they're going to get the name myRectangle. If you only wanted it, so if somebody else didn't want that name, you could copy the module and give it a different key, I don't know, rectangle 2, and it could have a different name. So you bind the arguments to a particular instance. And yeah, okay, that's just shorthand. And so this is actually how you now would run it. So I bound the argument. That doesn't actually matter because the name would just default to an empty string. And so what I do is I now create my inputs. I'm going to actually do a prism volume. I'm going to compute the area of a prism volume. And so that takes 3 dimensions. The first 2 are going to be used as the area of the base. The last one's the height. And I simply ask the module manager to run whatever modules under the prism key as a prism volume, and I provided those dimensions. And so what the module manager is going to do now is it's going to realize that our prism module needs an area module, and it's going to pull that rectangle module that we set as the default, and it's automatically going to provide that to the prism module, and then the dimensions are going to go into the prism module, and then the prism module is going to forward the first 2 to the area module, which now also has the name myRectangle because we bound it. So as you can see, the API is decoupled to what goes on inside. I mean, the user in this particular case does have to know what modules they're using, but it's assumed that the user has that kind of knowledge. So the SDE's API itself is largely targeted at a package developer. So it's really designed so that the package developer can quickly adopt other libraries, refactor their code, etc. It's not necessarily meant for the end user. The end user probably wants a far simpler API, probably actually just wants to go through a GUI. But it's our opinion that it's relatively easy to build those kinds of either domain-specific language or GUI on top of the SDE, particularly through the Python bindings. And that's sort of, I guess, the end of my tutorial. It's really that's the SDE.
Thank you, Ryan. We have one question from the audience here.
Sure.
Hi, Ryan. Thank you for the detailed introduction of the SDE API. Could you please describe how does that interface improve NWCam scaling abilities, particularly to the exascale platform? And second question, what role that API plays in improving I/O performance of the application?
Okay, so let me answer the second one first. This has nothing to do with, I guess, I/O, assuming you mean I/O as in like writing to disk. That would, if you're going to do I/O, you do it in your module. Particularly on the exascale, we're really trying to avoid I/O, so I don't think any of our modules actually write to disk. So with regards to the first question, how this helps us is, in particular, so right now we're designing all of our modules for Summit. Summit's architecture's out there, it's public, everybody knows what it is. Aurora, which was just announced last week, I think, and the architecture's still relatively secret, other than it's Intel-based, is going to require different modules for performance. So the idea is we don't have to rewrite the entire code anymore. We can just focus on the sort of the bottleneck parts. So thinking, if you're familiar with the Hartree-Fock algorithm, for example, the bottleneck is always the J and K build, specifically the K build. And so if we're trying to get Hartree-Fock to scale on Summit and then try to get it to scale on Aurora, the first thing we're going to do is rework that K module. And again, the architectures are likely going to be different. I can't really say anything about Aurora. Odds are it's different. And so how we get performance on Summit is going to be different than how we get performance on Aurora. And so that means we need two separate modules. And we don't want the entire rest of the code to be coupled to that. And so that's really how this helps us get to the exascale, is it allows us to work module by module at getting to the exascale. Does that answer your questions?
Yes, thank you.
Mm-hmm.
Thank you, Ryan. I don't think we have questions on our YouTube chat. So I had a question with regards to the page that we are currently looking at. It looks like this is a documentation page. So where can people find it? Where should people go if they're interested in contributing to your project?
So the project itself is hosted on GitHub. Unfortunately, right now it is a private repository. We are really trying to get through this. We're having some licensing issues with Pacific Northwest National Lab at the moment, who is not approving our license. And until we get the license approved, we can't release it public. In theory, it will be released under Apache 2. We're hoping, and I've been hoping now for a couple months, admittedly, that this is going to be imminent. That we're going to go public. And so that would be a GitHub repository. You would just go to the NWChemX page. I think you can go there right now, but there's no public repos, so that's not really anything useful. And you would just follow then the normal GitHub procedures, fork the repo, and submit a pull request if you wanted to contribute. As far as the actual documentation, the plan is to host it on Read the Docs. Again, it's unfortunately a private repository, so I can't get Read the Docs to host it. Maybe if I had paid account or something. But at the moment, you have to just build the documentation locally and read it locally. But again, once it's public, the plan is to have it on Read the Docs.
Okay, thank you. And so on what platforms is this SD currently available?
So right now we are purely targeting Linux. A number of our developers use Mac and have told me that it works on Mac. I admittedly just a pure Linux person. At some point we will probably actually consider Windows, but all the supercomputers are admittedly Linux based, and so that is our top priority at the moment.
Thank you. Although I should clarify, I meant HPC platforms. I apologize.
Oh, so it works on Summit. That's the only one we've targeted at the moment. I presume it would work on others. Its actual dependencies are very minimal. Just a C++ 17 compiler, basically. And then it uses a couple header-only libraries that, should just compile. So.
All right, thank you very much. Let's switch to our final slide. Once again, thank you, Ryan, for the presentation. It was, I hope it was useful to those who are interested in contributing to your project and actually getting to know what actually this tool is about. So we have two upcoming webinars. One is next month, and the tentative title is Jupyter and HPC. And one more webinar in May, which is titled Sustaining Open Source Software and Their Communities in Computational Geodynamics. So with that, I'd like to thank all of you for joining us today. As a reminder, you will receive a summary after this webinar as soon as we process with the video. If you have any suggestions or recommendations, send them to us at bw-eot@ncsa.illinois.edu. So once again, thank you for joining us today, and we'll see you in the next webinar.